Hey, this should be the last lecture for this semester. So I'm going to go through some quick review and go through some of the problem, similar to the one that you see for your study guide. I just try to pick some like different, well, it's kind of exact the same problem, but it has like different writing or different pictures. Exam is on Monday. I'm trying to give you office hour on Sunday afternoon. So I sent out an email already. If you wanted to jump in, have any question that you wanted to me to explain, then you can join. But you can still send me the email if you got stuck or you have question about some of the problem you wanted to talk, and then we can make appointment during the weekend as well. So that's the plan for before the exam. And wanted to remind you, if you want to get a free sandwich, then let me know and post it in the discussion forum. Even if you're not going to come before 1, that will be fine, because I just need to know how many people want it, then I can purchase that. But if you didn't come in around 1, then it probably is, well, so which is cool anyway. Okay, so that is the things I want to remind you. Let me share the screen about the notes. Okay, share the screen. Can you guys see the screen? Yeah. Okay, I guess. Okay, so the final exam, there's 6 calculation problem. One of them is like the extra credit for your previous exam. I just picked a few questions over here and go through these things. First one that you see here is a kinematic problem. When we do the kinematic, we define how the velocity, acceleration, and we also define like instantaneous, average, velocity. So the main difference between the average and the instantaneous is how long the period of time that you are looking at the velocity or acceleration. So if you look at a very small little time period, which you just take a snapshot of the motion, then that give you instantaneous. Most of the time it's if you have instantaneous, most of the time that you have an equation. But if you have a graph, then we usually just ask you about the average. So in this problem here, you see a graph, it describes a car is traveling back and forth. Why does it go back and forth? Because if you look at the plot, first thing you have to be careful about is that what is the graph is graphing, is graph with what versus what, right? So now the x-axis is time, the y-axis is v, which v is the velocity. So v is meter per second. Then you know this is a velocity time graph. If this is not a velocity time graph, then you have to be careful how you're going to deal with that. We have position time graph, we have acceleration time graph as well. They are related, okay? Now this particular one is velocity time graph. And it tells you there's 3 different section or 3 different interval, the A and B and C. So A is from 0 to 1, which means from here to here is A. And the B is from 1 to A, which is all the way down to the end. This is a B. And C is from 1 to 3, so C is from here to here. So try to look at this in 3 different intervals, and how do we rank the magnitude of the displacement, the average velocity, and average acceleration. Okay. Now, just on this graph, there's a lot of story that you can tell. The slope or the value, they all represent different things. The area also represent different things as well. So for the velocity time graph, the slope represent the acceleration, and the area represent the displacement. Okay. And it has positive, has negative. It depends on whether you are above the graph, the horizontal, or below the horizontal. So over here you have a positive on the top, and here you have a negative. Same for the area, it will be positive or negative. So over here, the first thing we wanted to look at is what is the displacement. The displacement meaning the area under the curve. So if you look at the curve, then we wanted to find the area for each one of the interval. For the interval of A, let's say A here, is the area, right? So let's look at the area of A. So the area of A is this part over here, which is from 0 to 1 second. This is an area of A. So this is the area that we're trying to find, which represents the displacement. Displacement meaning the change of the position. Okay, so then what is the area of this? Well, the area is simply just a rectangular area, and that's 10 meter per second multiplied with 1 second. And that tells you this is a 10 meter. Okay, so here is the 10, and the time is 1 second, so that is why this is a 10 meter. If you look at the B, let's look at the B. The B is a little bit more complicated because B encloses all range of the time, and you have 3 different places that you have the area. So if we now look at the B, and the B has this part here, and this part here, and this part here. Okay. Now be careful when you calculate the area. This is a positive, this is a negative, this is a negative. Okay. So the first one here from 1 to 2 seconds, for 0 to 1 second, that is a trapezoidal. Now you can also use a rectangular plus a triangle, whichever that you think that you know how to do the area calculation. I do it in this way. So let me draw the shape at here. I have this one, the trapezoidal, and the equation for the trapezoidal is that you have the sum of the 2 bases, and you divide by 2, then you multiply with the height. So my height is here is 10. My 2 bases, one is 1, the other one is 2. So the area is 1/2 1 plus 2, and multiply with the height, and that will be the area of the trapezoidal shape. So this one gives you 10 divided by 2 is 5, 5 multiplied by 3 is 15. Okay, so that's the first part. Now you also have the second part. The second part, this one here, is also a trapezoidal, right? This is one of the base, this is another base, and I also need to know the height. So 1/2. So the bottom part is from 4 to 5, that's 1 second. The top one is 3 to 6, that's 1, 2, 3, 3 seconds. And what is the height? The height is from 0 to -10. And when you multiply -10. That's why this is negative. And therefore, this number is going to be 1 plus 3 is 4, 4 divided by 2 is 2, 2 multiplied with -10 is -20. The last one is the small triangle at the end, and this is a negative. So that will be -1/2, and based on height, well, which think that you, well, let me make the negative to be the -5 of the speed here. So it's -5 multiplied with, this is a 7 to 8, which is 1, and that will be -2.5. Okay, so if you add them all together, you have a 15 meter plus 20, well, not plus, that's negative, minus 20 meter and minus 2.5 meter. That result is -7.5 meter. Okay, so that's the 7.5. And then if you look at the C is from 0 to 3. That actually is the trapezoidal, which is this one here. Then this is simply just 15 meter. Okay, now the question is to ask you to rank the magnitude of the displacement. So we only look at the value, we don't look at the sign. That's what the magnitude means. So if you want to rank the magnitude of these three, then that would be A greater than, no, not A, actually is C. So it's going to be C greater than A greater than B. That will be the rank for the displacement. All right, just if you have question, let me know. Otherwise, I'm just going to continue on this one here. The second one we do is average velocity. Okay, so what is the average velocity? How do we define average velocity? Average velocity meaning that you have a velocity of the last or the final minus the velocity of the initial. You divide by the time, how much time it passed, which, or you can say the time of the final minus time of the initial. That's how we define the average velocity. Okay, you look at the overall range of the time, and then you find the starting and the final one. Let's look at the A. So if the A, which from 0 to 1, let me clean this one up a bit. Okay. Okay, for the A, we start from time equal to 0, that is 10. When you go to 1, it's still to be 10, right? So, wait, I did this one wrong. This is a average. I was writing the velocity acceleration. So let me change this one to A. This is an acceleration average. If you look at the velocity average, this is not. The velocity average is the displacement over the change of time. Okay, so that's the average velocities. So if we do the average velocity for the interval A, our displacement that we calculate, which is 10, so you have the 10 meter and divide by the change of time. Now the change of time is from 0 to 1 second, so that's 1 minus 0. And in seconds, so that's 10 meter per second. Okay, and which makes sense because you didn't actually change the velocity. So the average velocity is the same as the velocity of the starting and the end. They didn't change, it's a constant velocity, so it's 10 meter per second. Similarly, if you do the B, that will be the displacement, which is negative 7.5. And how much time does it take? It takes 8 seconds. So this is 8 seconds. And that is the average velocity for this one here. That will be negative 0.94 meter per second. And C is 15 meter and divide by how much time? It's from 0 to 3, that's 3 seconds. So that is going to be 5 meter per second. And that's the velocity. Now, if we look at the magnitude of that, now we don't care about the sign, then in this case, the rank of that will be A greater than C greater than B. All right, the acceleration, you look at the velocity. So for the A, starting velocity is 10, final is 10, starting is 10, divide by the time, and time is 1 second. It's 1 minus 0, so it's 1 second. So that is 0. Okay, and which also makes sense because this is a uniform velocity motion. When velocity is a uniform, you don't have acceleration. So the acceleration equal to 0. For the B, that we look at, our starting is this one here is 10. Our last speed at here is negative 5. So you have negative 5 minus 10, and you divide by the total time, which is a second. And that is your result. Okay, so this one turns out to be negative 1.9 meter per second squared. Okay, same thing for the C. And think about this by yourself. Can you write this down? What will be the final one? C is here. This is the final. And final is 0. And starting is 10 minus 10. And you divide by 3 seconds. So that will be negative 3.3 meter per second squared. Okay, again, if we only look at the magnitude, we don't care about the sign. In this case, it's a C greater than B greater than A. And that is the answer for this one. Okay, question about this. Okay, let's look at the second one. Second one, I'm going to show you about the work and energy. There's another topic related to this one, which is called the impulse and momentum. The equation about those are always going to be the conservation law. So the work, let me define work. Work is equal to the force times the displacement along the directional force. That's the work, okay? The energy, we have kinetic energy, that is 1/2 mv squared. We have a potential energy, U sub G is mgh. We have U sub S, which is a spring, that's 1/2 kx squared, where x is the change of the length. Okay, so that is our equation for the work and energy. And here they give us a spring and also a block. They tell you the block on the table doesn't have a friction. Okay, that's a good sign that we don't need to worry about the friction. The friction is always harder to deal with. So there's no friction without friction. Then you have a block 0.6 kilogram. and travel with a speed 2.3, and it will stop over a distance of 0.18 once it contact with the spring. So what does that mean? That means we can write down all this information. This one, the mass is equal to 0.60 kilogram. Okay, this is not weight, this is a mass. The velocity is 2.3 meter per second. And because there's no friction, so this velocity will not change. It will keep on going at the same velocity. When this block hits to the block, which hits to the spring, what happened to this one is that block is going to compress the spring. So the spring will be like this, and spring is going to be pushed by this much of distance. And this distance is 0.18 meter. Okay, so that's the situation they give you. But they're asking different things. Let's just look at this one here. The first question that we'll ask is that, so the one I wrote here, just try to help you to understand how to solve it. What is the initial kinetic energy of the block? The reason that we ask this one is that in this working energy method, or even for the impulse and momentum problem, you always wanted to start by identify what are the information you can collect from the initial, what are the information that you can get from the final situation. And so when we define initial and the final, then we say this is the state, and each one have a different state, and we collect information from the state. And if we look at the block, they just say, okay, when the block is here is the state one. When the block compressed at here, this is the state two. So for the state one, you have, and the system that we're looking at is not only just the block, it also includes the spring. So the system is the block with the spring. And let's make a table to find those information about the energy. So we have two different states. We have a state one, we have state two here. And what kind of a work and energy do we have? We have energy. We have a kinetic energy. And this kinetic energy is the kinetic energy of the block. We also have a potential energy. But this potential energy is not the potential energy of the gravity. This is the potential energy of the spring. So this is about the spring. And in this case, we don't have work, okay? If you wanted to have a work, then either you have a friction or you have someone that is given the force to push the block or pull the block. That will add the work. In this case, we don't have that. So there's no work here. The kinetic energy of the block depends on the velocity. So you look at what is the state one velocity. The state one velocity is this. So my kinetic energy for the block is 1/2. And m, which is 0.6, and v, which is 2.3, and the square. So that is actually your initial kinetic energy. Your initial kinetic energy is 1/2 times 0.6 times 2.3 square. I didn't write the unit, but this one should be in kilogram. This one should be meter per second. if you use these unit for the calculation, then the result is going to give you the energy in joule. So multiply these all together, they give you a value. Let's see what the value looks like. That give you 0. Wait. Okay, I didn't calculate that. But if you multiply all together, that will be the energy, okay, of the kinetic energy. The second question I ask is this: what is the spring constant of the spring? Okay. So because we want to find the spring energy. Now, what is the spring energy at the beginning at the state 1? It's 0, because at the state 1, nothing touched to the spring. The spring doesn't have any of the force acting on the spring, so there's no energy at all. It is pretty much relaxed on the table, so nothing is moving or pushing on that, so the energy will be 0. When the block push to the spring and travel 0.18, or the compress the spring for 0.18 meter, that will be our state 2. Okay, so it said the block stopped over that much of distance. When it stopped, meaning the block has a 0 velocity. When it has a 0 velocity, the kinetic energy will be equal to 0. But where the energy goes to? The energy goes to the potential energy of the spring. So the potential energy of the spring is 1/2 kx squared. And what is the x? X is 0.18. What is k? We don't know. It wasn't given. So that's the one that we try to find. Okay, now we can use so-called conservation of energy to find the answer. The conservation of energy, meaning the initial kinetic energy plus initial spring energy equal to the final. Okay, and there are a lot of things is equal to 0, right? We know this one equal to 0. This one equal to 0. So what we have from here is that initial kinetic energy equal to your final spring energy, where this is the initial kinetic, this is the final spring. Then you can write 1/2 times 0.6 times 2.3 squared has to be equal to 1/2 k and 0.18 squared. That has to be equal. Okay. You can solve the 1/2, then you find out, well, what is k? The k is equal to 0.18 squared. So 0.6 times 2.3 squared divided by 0.18 squared. And that is your k. And that turns out to be 98.0. The unit for the spring constant is Newton per meter. So that's how you get this value here. Okay, and that's spring constant. Now, what the problem asks us at the end is this one here. It tells you what distance would a 1.3 block travel and make the contact with the spring and stop the spring. And they wanted to find out what distance it will travel to stop it. And they tell you the starting travel velocity is 3.1. So what I tell you is that your initial kinetic energy is 1/2 and it become 1.3 kilogram. Your velocity will be 3.1 meter per second. And this one, if you want to find out the x, you can also make this one equal to your kinetic and your potential energy for the spring. which is 1/2 times K. Now I know K is 98. And what I try to find is the X. So you make this one equal to X 1/2 m KX squared, then you can find out the X. So if you solve this one, then X is equal to 0.357. And what is the unit for this? This is the displacement that should be meter. The same thing as the above one at 0.18 meter. Okay, any question about the second one?
No.
Okay, let's look at the third one. The third one is about the buoyancy problem. So the buoyancy, there's several principle and you have to remember Archimedes principle always tell you the buoyancy force equal to the density of the fluid times the displaced volume times the G. So that is the buoyancy from the Archimedes principle. Now there's several situations, then it will tell you your buoyancy force based on their weight or some situation. The first one that you see is the float. That means it's float, it's not moving, it's just float. It could be partial or fully submerged in the fluid. So in this case, A is float, is a partial float. What about B? In this case, B is not. B is not was because you tied a string. If you tie a string, then it's not like a freely float, then it's not going to work on this situation. C is not float, it's actually sink down to the ground. So C is also not. The D is also not because it's also tied with a string. So if you look at here, the only situation you have the weight equal to buoyancy force is the block A. For the floating, meaning it's actually moving upwards. That means the weight is smaller than the buoyancy force. Then you will have the floating. Similarly, if the weight is greater than the buoyancy force, then is going to be sinking. That means it's actually it's moving, right? But in this picture, we cannot show you the moving, so we didn't draw those moving situation. The sink one is the D, is the C, so which is this one here. If you have anything that sink to the bottom, then you're gonna have abnormal force that will be coming out from the bottom of the tank that apply to the block. So the weight is going to be equal to the supporting force plus the buoyancy force. That is the situation for the block C. Now, if you look at the D, then you have a string, so you have to consider about the string. Now, it depends on which direction the string is. Then the direction might be different. So let's draw a free body diagram for these two situations and see the difference. So I'm going to draw the free body diagram for the B. So for the B, you have a buoyancy force going upwards. You have a weight going downwards. What else? Well, you have the string. The string always go away from the object. So this is a string force. That is the situation of B. Now, if you look at the D, what we know about weight is the weight always going downwards. So this is the weight. And our buoyancy force always go upwards. What about the string? Well, this case, the string is tied on the top and as get away, then how do you make it get away? There will be, this one will get away. Okay, so that is how you are going to write the string tension force and this situation. Okay, this is important because if you want to solve the problem, you need to know the equation of motion. You simply just need to find out what is the net force that come out from these two different situations. Okay, now let's look at the question right here. Rank the buoyancy force if all of them had the same mass. Okay, so we know for the A, it's the mass of A. So this one is going to be just the mass. Okay, so let me write the M here. What about block C? The block C, we know this is the situation, and this situation tell you the weight is equal to the normal force plus the buoyancy force, or the buoyancy force is equal to weight minus n, the normal force. So that is not equal to the weight. I should write the weight here. So this is FB equal to weight. C here, the FB is equal to the weight minus n. So it's very obvious that the buoyancy force of the B should be great. Buoyancy force of the A should be greater than buoyancy force of B. Okay. Now we probably won't be able to rank all of them because there's certain situation. Oh, well, let's take a look. Maybe we could. Okay. So what about B? If you want to find out the buoyancy force of B, then you write the equation of the net force. For the block of B, you have buoyancy force equal to the tension plus the W. So would this one has a larger buoyancy force than the A? Yes, because the buoyancy force for the B is the weight plus the spring plus the tension. So the buoyancy force is actually larger. Okay, so this one here, the B is going to be greater than the A. What about block of D? Then you look at the equation. Now the equation becomes F of B plus T equal to W, which means the F of B is equal to W minus T. Okay, because it's a minus, meaning it's going to be less than its weight. So if we rank A, B, and D, if they have the same mass, then which one is the largest? It's block B. Block B is T plus its weight. And the next one will be the A. And the next one will be the C. Are we looking at, oh, the last, why do I write the D? Okay, yeah. This one will be the D. Okay, I cannot compare with the C because this is a normal force. This is a tension force. I don't know which one is larger. Unless we got more information, then we can do calculation. So that's the ranking for the same mass. What happens if they have the same volume? Well, if they have the same volume, you use Archimedes. Okay, use Archimedes. The Archimedes will look at how much of the volume actually is submerged in the liquid. Okay. So if that same volume, and you can see A only have a partial of the volume inside of the fluid, so it's going to have a last. So A is the smallest one. And B and C and D all greater than that because they all fully submerged. Now, they have different buoyancy force for the B and C and D. If they do, what is the ranking? So to answer this, actually, they all have the buoyancy force because they all submerged, fully submerged in the liquid. So they are all have the same amount of the buoyancy force, and that is greater than A. Because we're looking at the Archimedes principle, we're looking at actually how much change of the volume due to this object that you sent, that you put it. Okay, so B, you go to C, you go to D, but they are all greater than A. Okay, now the last thing here, I'm just have like two little calculation here. I try to find what is the normal force on the C, what is the tension force on the D. If you want to find a normal force of the C, you have to use the equation of the force. For C, we have this relationship, F of B equal to W minus normal force. And what we try to find is this one here. So the normal force is equal to the weight minus F of B. And you look at equation here, do we know the weight? It doesn't give us the weight, it gives us mass. So the mass gives me the information about the weight because it's mass times the G, then that will be your weight. But what about the buoyancy force? When you have this situation, the buoyancy force is no longer equal to the weight. You have to look at how much of the volume is actually submerged in the liquid. And do we have those information? What is the volume of this block C? Well, the volume of the block C can use this equation to find, this is the density. We define density to be, if this is a mass density, that will be the mass divided by the volume. So we were given was the density of the block, the mass of the block. So density of the block, mass of the block, then you can find out the volume of the block. Okay, that just equal to 3 kilogram divided by the, wait, no, let's see, yeah, it's mass divided by the density. So the density is 1500 kg meter cube. And then you put this one here. So you put the V block and this here. So let's write down the buoyancy force based on the Archimedes principle is this one, is the rho of the fluid, which is a 1025. And the V displaced is this one here, is the block one. Let's see. Rho V, yeah, the V is that one. So V is 3 divided by 1500. And what else? And the G is 9.81. Okay, so with this one here, then you can find out the answer of your N. So this N here is equal to these things over here. And then you can do the calculation. Then similarly, if you want to find the D, so for D, you need to write down the equation, which is this one here. So we have F of B equal to W minus T. Okay, then how do we know the, we try to find the tension force, right? So if you want to find the tension force, then let's write T is equal to W minus F of B. And what is W again is going to be mass times the gravity. And what is the F of B? The F of B is the rho of the fluid multiplied with the volume of the object. So what is the volume of the object? Is the same way that we calculate from the previous one. You have a 3 kilogram of the mass, but the density is 1,000 instead of 1,025. You put 1000, that's 1,000 here. Then you multiply with 9.8. That's how you get the buoyancy force for this one. Okay, question about this? Okay. All right, the thermal equilibrium, this one I'm going to skip this one. Then you, this one is exactly the same as the study guide, so I'm going to skip this one. Just know that you have two ways you can change with the heat. You can use the heat to change temperature. When that is the case, you use this equation. When you have the change of state, you have to find the latent heat, and these are the equation. It depends on, it's a fusion of the evaporation. You use different value. The change of temperature, at this case, you can use change of Celsius or change of Kelvin. It will all give you the same result. C, the big C here is the specific heat. So is the heat capacity. So if we give you this problem, we will give you those numbers. The sign is also important, positive, negative, add heat or remove heat, or absorb heat or release heat, is based on the sign convention. ISO process. This is another one that you're definitely going to have this one, and I hope everybody will do it right this time. A lot of people did it wrong. So the equation related to this one is the first law of the thermodynamics, which is the change of U equal to Q minus a W. The Q and W that defined by how they do the work. This is the gas to environment. And this Q here is the heat from environment to the gas. Okay, meaning is the energy that flows from the outside goes in to the gas. And then if you look at the solution or the example of video, then we tell you how you calculate these things, right? So first thing you need to calculate is this U, internal energy. That means is the energy of all particle could be air particle, most of the time it's going to be the gas particle. And each one of particle is moving with certain amount of kinetic energy. You add all them together, that is the internal energy that we're talking about. Internal energy also include the potential energy as well, but we are more interested about the kinetic energy because potential energy probably is around the same. So, but this is represent total energy. That equation to find this is equal to 3/2 nRT, or 3/2 P times V. There's some other way that you can find this is a 3/2. If you know total number of the air particle, you divide by Avogadro number and times RT. That is also equal to that. And we also have some other way that you can write, like you represent that in like Boltzmann constant, then this will be 3/2 K times T, right? So these are the things that the equation is given in your exam. That's potential energy. So for each one of the point, let's say this is the point 1, let's see. This is point 2, this is point 3. The easiest way to find this is simply just use this equation here. 3/2 P times V. So if I want to find U sub 1, that is 3/2. And you look at the 1.1, what is the pressure? The pressure is this value. So pressure is 1 and times 10 to the negative 2. And what is V? V is 1. So that gives you the energy of internal energy of 0.1. Okay. All right. So that is 1.5 times 10 to the negative 2. And the unit for this is joule. You can do the rest of them. I'm not going to spend time to talk about each one of them. So the next one that I ask you to do is to find temperature. How do we find temperature? And if this one is an ideal gas, you can use the ideal gas law. Ideal gas law is PV equal to mRT. Now, it's very easy to read the P and V. And in this equation here, the only thing that will change is the P and V. N is a constant. R is a constant. Well, N is the number of mole, unless you change the number of the mole inside of the system. Otherwise, the N normally doesn't change. And therefore, you can find the temperature that is equal to PV over N times R. What is the N? If N is 1 more, then N is 1. And R is 8.314, I think. And it depends on what unit that you are using, then you have a different value for R. On the top one, you just simply multiply P and V. Again, it's going to be the same as the previous one. Your P was, which one we're looking at? Oh, let's just try to find the 0.1. If we look at the 0.1, then pressure is 1 times 10 to the negative 2. So it's 1 times 10 to the negative 2. And what is V? The V is 1 meter cube. So that's how you find temperature. This is in degree, not in degree. This is in Kelvin. Okay, so in Kelvin. Don't assume this one is in Celsius. No, it's not. So this is in Kelvin. That's how you find temperature. Now, the 1, 2, 3, they all have a different temperature. The next thing you need to know is how to find work. Work is very similar to the kinematics that we talk about. The work is going to be the area under this PV diagram. Okay, there's a sign issue. If arrow goes to the right, meaning this is an expansion, and the work is positive. If the arrow goes to the left, this is a contraction. When this is a contraction, the work is negative. Okay, so with that in mind, another thing you need to know is, oh yeah, so either you use the area or you use this equation. So these two pretty much represent about the same thing. It's just that one is using the linear algebra way to write it, and on the right hand side is in the calculus. If we use the calculus, I know the function of p with respect to v, then I can also do this integration to find the result. For this case, you can see they give you an example work equal to negative 400. How do they get this number? They get this number from 0.1 to 2. And you cannot use PdV. The reason is because P is not a constant. Okay, the change of volume, you can still find the change of volume is from 1 to 3. So volume increased 2 meters square. But what is the V? The V, well, I just said the V is increased 2 meter cube. The P is that P is not constant. Okay, so you cannot use P times delta V because P keep on changing. So the only way you can do it in this case is to find the area under. Okay. And you look at this one, it's not just this triangle. It's actually is the triangle plus the bottom part here. That is counted as the area, okay, in this case. So again, you can use rectangular plus the triangle. Let's do this one in this way. The triangle give us what? 1/2 of the base. The base is 3 minus 1. And the high is going to be 3 minus 1. That's the triangle. Then you look at a rectangular. This is a rectangular one. That will be easy. Just the width times the height. That is going to be 2 times the height, which is 1. And then you add them together. Oh, sorry, this is not just simply, oh, I did it wrong. Here, the P is 10 to the second. So it's actually, if you look at here, this is actually 100 and 200, etc., etc. So I should change this a little bit. This will be 2 times 100. And this one here will be 300 minus 200, minus 100. Minus. Okay, so that's how you find the area. This one goes to the right, so it should be positive. But why would this one go negative? Okay, this one is negative because it tells you what is the work done on gas. when you use this one here is the gas to environment. But this one here, the work is from environment to gas. So the sign will flip, the sign will be different. You look at here, it looks like the area goes to the positive, but because they change the way they define work, they have to flip the sign, and this positive will become a negative value at here. Okay, and in this problem, you also need to know what is the isobaric, what is the isochoric, what is the isothermal. There's another situation called adiabatic. Adiabatic meaning Q is equal to 0. If you have isochoric, then W equal to 0. Okay, work equal to 0. If you have isothermal, that means somehow a curve like this here maybe will be isothermal. That means the 2 points along the line, the 3 and 4, they have the same temperature. If they have the same temperature, meaning it's an isothermal process. Okay, so that is, the last one here is how do you find Q? So since you know this equation, the Q is equal to the change of U plus the W of the gas to the environment. What is change of U? Change of U is U sub 2 minus U sub 1 is the final U minus initial U plus this W. And then you can find the solution in this way. Okay. Sorry, I get over the time, but let me finish this one here real quick. This is an oscillation and wave problem. So you given was a graph, and they tell you this graph is an object with 1.2 kilogram, and it oscillates like this. And we're gonna follow. We're gonna look at this graph to tell a few things here. The first thing I ask you is about the type of the wave. So we have two types of wave. One is called transverse. The other one is called longitudinal. What kind of wave this is? This is a transverse. This is a longitudinal. Now make sure that you know what the difference of these two. The second question asking about the number of the cycle in this graph. So what is the cycle? The cycle meaning it's if you start from any point, and once it start to repeat itself, that represent one cycle. So it start from 0, so it doesn't go to here to start from 0 again. It doesn't repeat at a 0.2 second. It actually repeat at a 0.4 seconds. So this one here is one cycle. And do we have a second cycle? Yes, it goes from here to here. This is going to be the second cycle. So number of the cycle in this graph is going to be 2. What is the amplitude? So how do we define amplitude? The amplitude is the highest point away from equilibrium position. Our equilibrium position is at here. Okay, the amplitude is from the equilibrium to the peak, which is this one here. This is the amplitude. And the amplitude in this case is going to be 4. So this is a 4 meter per second. Wait, this is a centimeter. It's 4 centimeter per second. All right, the next one is that we wanted to know what is the period. So what is the period? How do we define period? Period meaning how much time does it take to complete one cycle? So if we start from here and we know the one cycle is right here, right? So how much time does it take? 0.4 seconds. So period is this. The next is the frequency. The frequency is very simple. If you know the period is 1 over the period. So that will be the frequency that you try to find out. So if you do that, that will be 2.5. And the next one is the angular frequency. What is the angular frequency? Angular frequency is omega. Omega has several different equations that you can equal to 2 pi f, 2 pi over t, and square root of a k over n if the system is the small simple system, like a pendulum system. You only have a spring with a weight, and that will be the equation that you can use. The square root of k over n. Okay, so if you calculate this, this will give you a value which is 16. The next one that we're going to do is the spring constant. How do we get spring constant? The spring constant coming out from here. So you have a W equal to 16 equal to square root of k over n. And do we know n? N is 1.2. So 16 squared equal to k over n, where n is 1.2. And k is something that you try to find. And with this, then you can find the result. So the k here is equal to what, 300? Okay, the next one here is that they tell you if the wave, if this is a wave, okay, this is not oscillation, this is a wave. It has a wavelength 0.5 meter, then what is the wave speed? Okay, so what is the wave speed equation? For the wave speed is equal to lambda times f, the frequency times the wavelength. Do we know the frequency? We just got the frequency, which is 2.5. What is the wavelength? The wavelength is 0.5, so this is going to be 2.5 times 0.5, and this unit over here is going to be meter per second. That's how you get the wave speed. The next one is, what is the maximum velocity and acceleration? And this one, particularly for the honor section, you need to know how we can actually write the equation for this motion. So if we have this one here, the model of the motion is some kind of cosine function. So this is the position. Okay, the position is going to be amplitude times cosine omega t plus some phase angle, and we're going to ignore by assuming everything starts from the highest point at the beginning. And the amplitude is what? The amplitude in our calculation, we find out amplitude is equal to 4. And cosine omega t, what is omega? Omega is 16. So that's your position. You also can find the velocity. So the velocity is the differentiation of the position over time. So on a section, you should know how to do this kind of things. So you are taking the differentiation of this number over here. What is this value here equal to if you take differentiation? 4 is a constant, 4 doesn't change. Then you have the d cosine over dt that should be equal to negative sine. And then you also need to take differentiation of the things inside. So that will give you 16. And therefore, this is a negative 64 sine 16t. So what is the maximum velocity? This is the maximum velocity. 64 is the maximum velocity. Another one is the maximum acceleration. You take another differentiation and you will find out the acceleration. Okay, I'm not going to do it at here, then you can do it by yourself. Now I'm looking at the energy one. What is the total energy of the system? If you remember last week, we talked about total energy of this kind of system. The total energy, we use the E to represent it. The total energy is 1/2 K A squared. K is the spring constant. A is the amplitude of this motion. So this is 1/2 of K is 300. A is what? A is the amplitude of that, which is 4. And that is the energy of this one, total energy. Okay, now the last one of this review is to find out potential kinetic energy when T equal to 0.25. How do we do that? Well, this is the graph. 0.25 is not here, is somewhere, not at here, is here. This is 0.3, this is 0.25. If you want to find the energy, what you need is that you need to know position, you need to know velocity, because kinetic energy is velocity. Potential energy depends on the displacement. So you need to know x, you need to know velocity. And this one give me x, right? But when you read from the graph, it's not very precise. If you really want to get value, you actually need to use this equation. So let's see how we get the x from this equation. That means I need to find x when t is equal to 0.25 seconds. And you use this equation to find out the amplitude is 4, cosine omega is 16, and the time you're going to put 0.25. And that's how you find the position of that. Once you find the position of this 0.25 time, then you can find the potential energy. Potential energy is 1/2 of K x squared. So that is 1/2 times 300 times x. X is going to be this one here. Okay, put this number here, square, and that's your potential energy. Now, what about kinetic energy? I need to find the velocity at a 0.25, but there's another way you can find it, because the total energy is equal to the potential energy plus the kinetic energy. I know my potential energy here. I know my total energy, then you can find out the kinetic energy. Kinetic energy is the difference of the total energy minus the spring energy from here. Then you got the kinetic energy. Okay, so that is my review for you to take the final exam. Any question? All right, that is it. I'm gonna see you guys Monday.